Hey boys and girls, welcome back. Oh, I forgot to get some music on. That's what I was forgetting. I was sitting on the waiting screen being like, what am I forgetting? It's the music. That's what I was forgetting. Good morning, everybody. It's ridiculously early for me. This is generally an hour before the time that I would be rolling out of bed, in fact. But let's see here. Open directory. Keygen jukebox. Ooh, that's loud. I apologize. I apologize for the loud. I guess I may as well also get the TTS system running. I don't know if anyone will pay us a visit, but we may as well get the system on. Let's see here. Chat reader Zonos. You know, in the last stream, Zonos was the TTS system was going off, but no one, like, the audio didn't get captured. I don't know what was up with that. But yeah. I'm learning calculus for ML, and I need some help shoring up my weaknesses. Part of the reason for the long waiting screen is because I'm still kind of trying to figure out exactly what I want to do. But we're cooking up a prompt here, so I'll just I was hoping I would have this done before I switched off the waiting screen, but it got to about 5 minutes. I'm like, I better go live for real. So yeah, I'm learning calculus for ML, and I need some help shoring up my weaknesses. I have basically no math education, only know what... Thing is, it's not a little. Like, I know a lot, it's just I only know it in a certain context. So I'm great at applying calculus. I just don't actually understand any of the analytical solutions to anything, notation, or underlying theory. Today's goal is to get me to the point where I can...
System initialized.
Hi. Good morning, Lord Vader. You just go in the corner. Thank you. Where I can fully understand and implement gradient descent. The thing is, I already understand gradient descent. Like, I could implement it. Well, yeah, we'll just play it by ear and see how it goes. Actually, I think... Oh, this is just the description for human consumption. This should be... There we go. Today's goal is to get me to the point where I can fully understand and implement gradient descent. Gradient descent. I guess, yeah, that's the prompt. Let's go. Great goal. Gradient descent is one of those beautiful algorithms. Where the math and code mirror each other nicely, so you're already comfortable applying calculus and code. We have a solid foundation to work from. Let me start by understanding where you are. When you've used gradient descent in your ML work, what does the code typically do? For example, have you written something like weights equals weights minus learning rate times gradient? If so, tell me, what do you understand the gradient represents in practical terms? Why do you think we subtract instead of adding it? Right. So a long time ago, I did implement a MNIST recognizer from scratch using NumPy. When training with the gradient in that equation represents one way I can think to explain it is that the gradient represents how the weights need to change in order to make the model model produce an inference that is closer to the ground truth label in the data set, given the matching input from the training set. Label from the input label pair from the training data set. We subtract it because we want loss to go down, not up. I mean, that's the actual answer. I feel like there's more to it than that, but oh, you've got the right intuition. Let me probe a bit deeper on something subtle in your explanation. You said that the gradient represents how the weights need to change to make the model closer to the ground truth. That's close, but let me ask you this. If the gradient directly told us how to change the weights to get closer to the truth, why would we subtract it? Why wouldn't we want to move in that direction? Well, fuck, what am I taking the derivative? Okay. You said the gradient represents how the weights need to change to make the model closer to the ground truth. That's close. But let me ask you this. If the gradient directly told us how to change the weights to get closer to the truth, why would we subtract it? Because I don't know, that's just how it is. That's how the math works out, is that it's negative. Because sorry, I gotta finish my water here. Why is it so important that it's subtraction instead of addition? Well, I guess it is important, or else you wouldn't be bringing it up. When you computed that gradient in your MNIST code, what were you actually calculating? What's the relationship between the gradient and the loss function? Well, the gradient is the derivative of fuck, what is the gradient? I mean, well, the gradient is the slope of the loss landscape at the point we're exploring at the moment, isn't it? We subtract it because we're No, it's not. That's not correct. The gradient is... It's not the derivative of the loss function, right? It's the derivative of the inference function, isn't it? Am I completely off base here? Uh-oh. Okay, this is a super common point of confusion. I'm glad you brought it up. You're actually really close to something important. Let's untangle this. The gradient in gradient descent is the derivative of the loss function. Okay. It's the derivative of the loss function with respect to the weights, not the inference function. But I can see... Oh, the fucking loss function includes the... Right. Because the loss function... The inference function is in the loss function, isn't it? I can see why you might think it's the inference function, because the weights do affect the inference, which then affects the loss. It's all connected. Let me help you see why it has to be the loss function. Think back to what he said. We subtract it because we want loss to go down. If we're trying to make the loss go down, what do we need? Okay, so I actually overthought. I was right the first time. If we're trying to make the loss go down, what do we need to know? We need to know if I nudge the weights in some direction, does the loss go up or down? Alright. The gradient is the derivative of the loss function. We subtract it because traditionally we define our loss function so lower is better. If you for some reason decided to define your loss function so that higher is better, you would want to add the gradient, right? Okay. Exactly right. That's a key insight. Gradient descent is really gradient ascent with a minus sign because we're minimizing loss instead of maximizing something. Now let's dig into what derivative actually means, since you mentioned you can apply it but don't fully understand the theory. Imagine you're standing on a hill, your loss function. You're at some point and you want to know, if I take a small step in the direction the weight changes, how much will my loss change? The derivative answers exactly that question. It's the rate of change of loss with respect to weight. Here's a concrete example. If derivative equals 5, that means for every tiny +1 change in weight, loss increases by about 5. If derivative equals -3, that means for every +1 change in weight, loss decreases by about -3. If you're at a point where derivative equals 5 and you want to decrease loss, should you increase the weight or decrease the weight? If I want to decrease the weight because if the derivative is positive at the point I'm at, increasing x will increase y. I want to decrease y, so I decrease x. Perfect, you've got it. Okay. Well, I already understood this much. Okay, here's where it gets interesting for neural networks. In your MNIST code, you didn't have just one weight, you had thousands or millions of them, right? Well, I had a couple hundred, actually, but whatever. So instead of one derivative, you had a gradient, which is really just a fancy word for a collection of derivatives, one for each weight. Okay. Each entry tells you how does loss change if I wiggle this particular weight. Question: when you computed gradient equals compute gradient loss and weights in your MNIST code, you're computing derivatives of the loss with respect to each weight, but the loss itself was computed from the input image passing through the multiple layers comparing the output to the label. How do you think we calculate the derivative of the loss with respect to the weight of... How do you think we calculate the derivative of the loss with respect to a weight in the first layer when that weight's effect has to ripple through all those subsequent layers to eventually affect the loss? This is getting at backpropagation, the how, not just the what. That's what AutoGrad does, right? It uses the chain rule to track how every operation done to a number from being ending at being read in from the data set, ending at the output of the loss function, if affects it, and then we can use that to calculate calculate how changing that number will affect the loss function, right? Exactly, that's precisely what AutoGrad does. Now let's crack open what the chain rule actually is, since that's the mathematical engine powering all this. Here's the simplest version. If you have a chain of operations, the chain rule says the rate of change through the whole chain is the product of the rates of change at each step. Let me give you a concrete example. Say we have x equals 3, y equals x squared, so y equals 9, z equals 2y, so z equals 18. So now how does z change when we wiggle x? How does y change when x changes? dy over dx equals 2x equals 6. Derivative of x squared. Yeah. How does z change when y changes? dz over dy equals 2. Derivative of 2y. Yeah, so the derivative of x squared is 2x. Yeah. And the derivative of 2y is just 2. Because in an exponential, you can imagine that exponential curve, the derivative of x goes up the higher x is. But if it's linear, then it doesn't. It's just linear. It changes the same amount every time you increase it. Is this in a category? Oh, I didn't actually update my thing. Whoops. Alright, well, we'll just go just chatting. There. Okay. How does z change when x changes? Chain rule says multiply them. dz over dx equals dz over dy times dy over dx equals 2 times 6 equals 12. Alright. You can verify if x goes from 3 to 3.01, z goes from 18 to just about 18.12. Okay. Your turn. Using the same setup, let's check your understanding. A equals 2, b equals a cubed, c equals b plus 5. Well, okay. What is dc over dA? Equals dc over dA equals dc over dB times dB over dA equals the derivative of c equals b plus 5 is 1. Oh, wouldn't it be 0? No, it's 1. 1 because it's the derivative of b equals a cubed is 3a. So the answer is 3a times 1. Or just 3a. Almost. Okay. Shit. I don't remember. I don't know. Derivative of x squared is 2x. Oh. shit, I don't know. Well, x squared is x times x. X cubed is x times x times x. So... I don't think I was ever taught this part, but let me think. X squared is x times x. X is x times x times x. So x... I don't fucking know. I feel like it may be important that he told me the derivative of x squared is 2x to the 1. Is the derivative of x squared x cubed 2x squared? Because cubing something makes it change, like it makes it more exponential. You can imagine, you know, that parabola getting tighter around the y-axis. So... the higher the exponent, the tighter the parabola is around the y-axis, so it has to be doing multiplying something. The derivative of x is 1. Right? The derivative of just x is... What is the derivative of... What is the derivative of 1x? It's just 1. The derivative of x squared is 2x. Is it... Is the derivative of x cubed 2x squared? No. Okay. Good reasoning. You're thinking about it from first principles. Let me help you see the pattern more clearly. You've got these right. The derivative of x to the 1 is 1, which is 1 times x to the 0. Derivative of x squared is 2x, which is 2 times x to the 1. Now look at those carefully. Do you see a pattern in where the exponent number goes and what happens to the exponent itself? Here's a hint. Rewrite what you know. Okay. The derivative of x to the 1 is 1, which is 1x to the 0. I can see that there's a pattern. I'm just not sure what the pattern is. The derivative of x squared is 2x, which is 2x to the 1. Like, is it 3x to the square? To the 2? Isn't that what I said? It seems like if I just continue the pattern that it would be 3x to the 2. Bingo, that's exactly right. Bingo! The power rule is derivative of x to the n is n x to the n minus 1. Okay. You bring the exponent down as a coefficient and you reduce the exponent by 1. So x to the 1 is x, 1x to the 0 is 1. X to the 2 is 2x to the 1 equals 2x. X to the 3 is 3x to the 2 equals 3x to the 2. X to the 100 is 100x to the 99. Okay. But why? That's the thing. I don't get why, so I won't remember it. I don't have the intuition. Now back to our problem. A equals 2, b equals a to the cube, c equals b plus 5. What's the final answer for DCDA? It would be... well, it would be 2x cubed. 2x cubed times 1. Alright? Shit. Okay. Okay, hold on. Let me actually get it right. Or, well, 2a to the 2 times 1, or just 2a to the 2. Shit. No, it's 3. It's 3. It is 3. Okay, no. Yeah, I'm getting tired already. We're half an hour in. Wait, no, shit. Claude, sorry. I fucked up, sorry. 3a to the 2. Perfect. Okay. And if we plug in a equals 2, we get DCDA equals 3 times 2 to the 2 equals 12. You can verify. If A goes from 2 to 2.01, then C goes to 13 to 13.12, change of about 0.12. Now here's the big connection to neural networks. In your MNIST code, you had something like input, layer 1, layer 2, output, loss. When backprop computes the gradient of the loss with respect to a weight in layer 1, it's doing exactly what we just did, using the chain rule to multiply derivatives backwards through the chain. D of loss over D of weight in layer 1 equals D of loss over D of output times D of output over D of layer 2. This is why it's called backpropagation. We compute derivatives backwards from the loss to the weights, multiplying as we go. Well, I already knew all that, although I didn't... Okay, it's good to shore up the power rule thing. Okay, this is why, yeah. So in a neural network with 10 layers, roughly how many derivatives do you think we'd need to multiply together to get the gradient for a weight in the first layer? In the first layer? 10, right? 11. 11. 1 for each layer, plus 1 for the derivative of the loss function itself. Great intuition. You're thinking about it right. It's roughly 1 derivative per transition through the network. The exact count depends on how you structure things, but yes, for 10 layers you'd have something like 10 to 11 terms multiplying together. This is actually why vanishing gradients happen in very deep networks. If you multiply 100 numbers that are each slightly less than 1, you get a really tiny number. Okay, let's zoom out and connect this back to gradient descent. You now understand the gradient is a collection of derivatives, 1 per weight. Each derivative tells us how loss changes when we wiggle that weight. Wiggle, 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 wiggle. We compute these using the chain rule. We subtract the gradient to move towards lower loss. But here's something we haven't talked about. Why does moving opposite to the gradient actually take us towards a minimum? Think about it geometrically. Imagine your loss function is a valley. You're standing somewhere in that valley. The gradient points in the direction of steepest descent, uphill. If the gradient points uphill, what direction should we move to go downhill fastest? The opposite direction, which is why we subtract the gradient. Exactly, the gradient points uphill, so minus gradient points downhill. And not just any downhill direction, it points in the direction of steepest descent. That's why this algorithm is called gradient descent. Okay, now let's talk about something you might have wondered about in your code. Weights equals weights minus learning rate times gradient. Why do we have that learning rate multiplier? Why not just weights equals weights minus gradient? Here's a hint. Remember when I said the derivative tells you how much loss changes for a small step in weight? Think about what happens if you're on a curved surface. The derivative tells you to slope right where you are. If you take a huge step, you might overshoot the minimum, end up somewhere where the slope is completely different, even bounce uphill on the other side. Based on this, what do you think the learning rate is controlling? And why might we want it to be a small number like 0.01 or 0.0001? If we had a learning rate of 1, each sample we would basically massively overfit on each sample as we process it. We don't want the perfect network configuration for the individual sample we're looking at. We want the weights to slowly approach the weights for giving us the best result. Slowly approach the ideal weights for giving us the best result would effectively massively overfit on each sample as we process it. We don't want the perfect network configuration for the individual sample we're looking at. We want the weights to slowly approach the ideal weights for giving us the best result over all our training samples. Another way to look at it is if you imagine plotting a 2D loss landscape, having too high a learning rate might jump us over the trough that we're hoping we would fall into. The learning rate determines the influence of each individual, determines how, that's why nowadays we tend to decrease learning rate over the course of a training session. At first, you're trying to get the weights to a place where they work at all. Then, once you once you have that, you're just refining the fine details, so the influence of each individual sample should be smaller, so learning rate must decrease. Excellent. You've nailed several key insights there. Let me highlight the most important one. If you imagine plotting a 2D loss landscape, having too high a learning rate might jump us over the trough that we're hoping that we would fall into. This is exactly the core mathematical reason. The derivative tells you the slope at a single point. Mathematically, it's only perfectly accurate for an infinitesimally small step. The loss surface is curved, so as you step away from your current position, the slope changes. If you take a tiny step, small learning rate, the slope hasn't changed much, you move downhill. If you take a giant step, large learning rate, the slope could be completely different. You could overshoot or even go uphill. Your point about learning rate schedules is spot on too. Early on, the gradient is large and we're far from the minimum, so we can afford bigger steps. Later, we're in a narrow valley and need tiny steps to settle into the exact minimum. Quick conceptual check before we wrap up. In your MNIST network, you probably had something like, for batch and training data, predictions equals forward pass batch, loss equals compute loss, predictions and labels, gradients equals backward pass loss, weights equals weights minus learning rate times gradient. Can you now explain, in 1 or 2 sentences, what that backward pass function is doing mathematically? It returns a matrix of derivatives for telling us exactly how much changing each parameter will change the loss function output. For each, the matrix matches the shape of the model weights. Well, a matrix or array of matrices of derivative. A matrix or array of matrices or list of matrices of derivatives telling us how much changing each parameter will change the loss function output. The matrix matches the shape of the model weights, and the derivative that of each model of each parameter is in the same place as the parameter it matches to. Perfect, that's exactly right. The gradient has the same shape as your weights because there's a 1-to-1 correspondence. Each derivative tells you about one specific weight. Alright, let's bring this full circle. You now understand gradient descent from the ground up. The algorithm: forward pass, input layers, output, loss, a single number. Backward pass, use chain rule to compute d of loss over d of weight for every weight. Update weights equals weights minus learning rate times gradients. Repeat until loss is low enough. The math: derivatives measure rate of change, power rule, d over dx of x of n equals n times x to the n minus 1. Chain rule, multiply derivatives through the chain. Gradient equal vector of all derivatives. Negative gradient equals direction of steepest descent. Final challenge. Could you now sketch out in pseudocode or explanation how you'd implement gradient descent from scratch for a simple function like f of x equals x squared without using AutoGrad? What would you need to compute the derivative and update x to minimize f of x? Well, the derivative is trivial. It's 2x. So we would repeat it if we were... we could just compute the minimum analytically. It's 0. If we wanted to use gradient descent, we would compute our loss, which is just... if we wanted to use gradient descent, we would, on f, our loss is just f itself. We calculate the gradient of whatever x we start at as 2x, subtract 2x time learning rate from our single model weight as 2x, single parameter, and that will converge on 0, right? Absolutely perfect, you've got it. Let's write it explicitly. X equals 10, learning rate equals 0.1. For step in range 100, gradient equals 2x. X equals x minus learning rate times gradient. Loss equals x squared. Print step. And we can run this in our head, or we could actually run it. I don't feel like it. Run this in your head. X starts at 10, gradient is 20, so we would subtract 2, making x equals 8. Then gradient is 16, subtract 1.6, making x equals 6.4, and it keeps shrinking towards 0. You've now learned everything you need to understand gradient descent. The beautiful thing is, your MNIST code from scratch was doing exactly the same process, just with thousands of weights instead of 1. Yeah, so I get that. I kinda already understood that, but yeah, that was a good warm-up. Okay. I think we can call this session basically done. This was a shorter one, but to be honest, I'm a little exhausted already. So yeah, we'll call this here. I appreciate everyone who stopped in to view this for a little bit. I'm not sure how interesting this is for you guys. Honestly, this is mostly for me, and this streaming it is to force me to focus on it. But if you did watch this, I appreciate you. Leave a comment in the comment section below to tell me how you enjoyed this content. But yeah, if you care to watch this, come back and watch it. If you don't care to watch it, you don't have to. We'll be streaming Control-Alt-Ego in just under 12 hours. And that'll just be a fun gaming stream tonight. So I will see you all there. But until then, goodbye. I'll see you all next time.